So please welcome on stage Giuseppe. He's going to talk about how Kotlin can change developer experience with modern graphics APIs. Please.
Hi, thank you. As I said, I'm Giuseppe Barbieri. I am a graphic developer by Rino, who is working on a software called mCheck, which is a cat-like software for analyzing the visibility field of different types of vehicles. And basically, I fell in love with Kotlin some years ago, and then I started writing some utility lists to help the development with graphics. So let's get started. We'll start with OpenGL. I will assume that we are all Kotliners, and some of you might already know OpenGL and maybe Vulkan. How many knows OpenGL? Okay, Vulkan. Okay. So for the others, let's say this is much more about code, so you can still understand most of the stuff. So let's get started with OpenGL. So it's a really whole library, let's say, started in 91 with SGI. Then they left the development in 2006 and basically hand over to Kronos, which released a very big version, 3.0, in 2008. They also introduced deprecation mechanism and context. And the 4.1 is the last available macOS. This is a little shame. And the last release available for all the other platforms is 4.6, which was released on 2017, 2 years ago. Vulkan came a little earlier than that. So, welcome GLN. What is about? Basically about makes some, I would say, some massive use of inline classes, where basically you already know it's an integer, and most of the time it's an integer, but works like classes, and also enums, although they are not really available in Kotlin, but there's a little trick. Then also we have inline functions, so basically you write the nice code, and then everything, all the, let's say, I will not say ugly, but all the boilerplate code will be then replaced by the compiler. It's also object-oriented. So, as I say, on the inline classes, we have all the method. DSL, where you can easily wrap some scope, some, let's say, OpenGL object, and then inside the scope, do something nice. Functional programming, so you can pass around lambdas whenever needed, and there are also some convenience overloading function that basically take maybe some parameter, some, let's say, parameters which are quite obvious out of the equation, so we can have some more concise code, and it plays quite well with, quite nicely with another library, GLM. It's basically a part of the original C GLM. To get the best way is just to start showing code, and let's go through a very, very simple hello world program. So in this case, for example, we start our main, we define some variable where we have, for example, the program variable, then a numerator to identify the two buffers that we are going to use, one for the vertex and one for the element, then the actual variable, which is under the hood, it's direct int buffer, it's native memory. Then we have one integer for the vertex array and two for the uniform, the so-called MVP for the model view projection matrix, and one for the diffuse color. Then let's dig into our first method, init program. Okay, here you can see in our function we start just. I will show you first the plain way to do it in Kotlin. So we first create our program, then we want to create our vertex shader. We have another function for that called init vertex shader. We go inside our init vertex shader. We can define here the source. This is a pretty standard shader where we have, for example, matrix, two then incoming attribute, vertex attributes. And here Kotlin makes very nice because first we have the triple quote. So compared to Java, this is already a very nice point, very nice advantages. And if we want, we can also inject, as you see in the comment, we can inject some explicit vertex layout, like for example position. Then we have also one for the color. We have an outside code for the color that will be linearly interpreted by the segment shader. And then in the main, we simply multiply the incoming position by the matrix. We assign to the GLSL position, and then we also pass the color. Then we create our vertex shader. We need to pass, of course, the type of the vertex shader, the type of the shader that we want to create. In this case, vertex shader. Then we can have a generic init shaders where we give the object we just created and the source. In the init shaders, we receive, as I say, the shaders and the source. So first, we want to set the source to the shaders. We want then to compile the shaders. It's a lot of redundancy here. Then we want to check if, of course, everything went fine, or we want to know if there was some problem. So we retrieve the compile status. GL get shader I means that, of course, we will get an int. Then we need to, for example, check this int against one OpenGL constant, like GL false. If the compile fail, then we want to see what went wrong. So we want, of course, to retrieve the info log, but to retrieve the info log, we need first to retrieve the info log length. And this is what we are doing here. GL get shader I, we pass the shader set, and then the constant info log length. We return an int. Then with this, we can call GL get shader info, which will return automatically a string. And then finally, we can throw our nice exception with the reason why the compilation failed. Then we can come back and we can return our vertex, which is an int. So how can we make this nicer? First, we will return from the init vertex shader a GL shader. This is an inline classes. The source is the same. Let's comment out for space problems. Then our original GL create shader will be converted to a static function on the inline class. So we want a GL shader, and we call create, passing, in this case, vertex shader is, you can think about like an enum. Then what we do here is basically we scope the GL shader, and then we can simply type much shorter code because we scoped it, so we know what this is going about, and we don't want any more redundancy. So we call simply source. Maybe this is unfortunately naming. Then we compile our shaders. Compile status. This is also nice. We are inside these, let's say, inside these scopes. So compile status is just, let's say, custom get variable, which will return, of course, the compile status. And we already know that the compile status should be a Boolean. So immediately we can return directly a Boolean. And then also the info log. I don't want to write all the boiler code. So I want to hide in the library. I just want to type GL shader info log, and then I retrieve all the log that is telling me what went wrong. So we saw here GL shader dot create vertex shader. Question is, what is this vertex shader? It's an inline class or a numerator? Well, it's actually both, because although Kotlin doesn't have yet inline enumerator, there is an issue on utrack, which I personally hoping to implement also inline enumerator. It's going to take some time. Hopefully one day we will get them. But in the meantime, there was a user, I don't remember anymore the name, but on the forum, on the Kotlin forum, wrote these nice tricks where we can basically use inline classes as an enumerator. There's just one disadvantage, let's say. Basically, the end user can create some additional enumerator, but of course, we want to play nice, so it's cooperative environment, and I mean, the user will not hurt itself and create an additional, maybe wrong enumerator. Then in our init, we come back to the init program. We just came back from create a vertex shader. Fragment is basically the same. I will not go inside because of a matter of time. Then we have to attach the vertex and the fragment to our program. In this case, for example, we bind the attribute location like position and color to some parameterized variable. And then we link our program. Let's, for a moment, pause here and see what this can become. So, program can be also an inline classes where we call basically GL program create, and then we call apply. Here, GL program will be scoped again. We call our corresponding create vertex and fragment shader, which in this case they will return inline classes instead int. Then we can use, for example, the nice overload operator from Kotlin to attach the vertex to the program. We can then, instead all of this stuff, GL binding attribute location blah blah, we can simply type the string. We are inside the scope, so we offer an extension function on the string that will, when will be set, it will be automatically called GL bin attribute location behind the curtains. So it's more like, I would say, natural. Then we link, just one call, and then we continue. We continue. Here, instead link status, we have, as before, just one variable because we are inside this block. Also, info log is just one line. Then we detach the shaders. It's not mandatory, but if you want to do the things clear, we detach them from the program, and then we simply delete the shaders. Since they are inline classes, we have a method available on the inline class itself. Honestly, you can do all of this with just one line. Using GL program init from path, you give the path of the shader source, and then the library will look through in this path for, you give up to the name of the shaders. Then the shaders need to have all the same name, and then through some standard shader extension like vert, frag, geom, test, and so on. We look if they are available. If they are available, we load them, and then it will compile into the program. Also, it will look in the same directory if you have any import on any additional shaders. Remember when we had to bind the attribute location? These, if you remember, need to be done before linking the program. So how can we do? We just pass them as a lambda at the end of our init program. And this lambda will be, of course, served to you with a program base. It's an object. Basically, offer you all this nice stuff like attribute with an extension variable on a string. And this will be called before the link program. Then link program, blah, blah, return the GL program to you. Everything nice and puffy. Okay, now init buffer. We go in the init buffer. This is pretty standard. We generate the buffer. We bind the buffer that we retrieve from our buffer variable using the numerator, just to make it nicer. Then we bind to the GRarray buffer target. We upload the position. We detach the buffer. Then we do the same for the element, and then we check the error, and we come out. So here, the buffer, we can basically generate them in just one line, we scope them. Since we scope, we can just use the numerator to retrieve the corresponding buffer. We bound it, and then we pass lambda, what we call, for example, just data position data. Everything is already known. We know the buffer, we know the target, no need to redeclare them. Same for the element, and so on. At the end, the buffer will be detached. Check error. Init vertex array, we do the same. Generate the vertex array, bind. We need to bind the buffer. We need to call a GL vertex attribute pointer where we give all the stuff to specification for our vertex layout. Then we detach a bind buffer, and the vertex array required to left bound the element array. This is what we do. We enable, we detach, we check the error. What we can do, we can call gen vertex array. We give the reference to our inline function. This is also something really cool in Kotlin. We bound it, we scope the buffers, we call the numerator bound on array. GLN offers some predefined layout, just post2 call spree set will automatically call all the lines that you see above. We bind the element, we enable, we check the error, and we come back. Then here in the render, we basically have a window size lecture heap position, where we calculate our projection, matrix, view, and MVP matrix. Then GLN offers you some overloading function like this GL viewport window size, set a clear color, clear depth, then we clear the corresponding buffer, and we go to the next stuff. We use the program, we retrieve the memory stack in order to allocate our matrix in native memory on the thread stack, and we bind the vertex array, draw element, unbind, unuse the program, return true. This can be done in the following code: program, used, we enter, just GL uniform MVP, and we give the matches. Everything will be done in the background. Vertex array, bound, as before, draw element, just pass element. Triangle is the default type primitive, and all the rest will be retrieved from the, in this case, element is an int buffer, so we can retrieve the number of elements that remains, the type, sign int, so on, sign int, and then the pointer at the end is defaulted to 0. Return true. At the end, we can just call the corresponding delete on the stuff. So with DSA, we can basically what was before, like GL buffer parameter get translated to GL get name buffer parameter. With GLN, you simply call buffer immutable storage on the inline class itself. Pretty natural and standard. So Vulkan, it's not only a cross-platform rendering, but also computing API. We're supposed to also, let's say, take over OpenCL. Really low overhead. You have more than 1,000 lines for a single hello triangle. Built upon Mantle, donated by MD. Was released in 2016, and the last release was at the beginning of this year. We have basically also inline classes, menu, inline functions. It's object-oriented. All the VK object has a lot of function on there. Functional programming and convenience overloading, low function. So where basically we call the very end function of the LVGGL binding just before going to the native, and then also play nice with GLM. Let's go just through a very short stuff. So just like create instance, we want to have a validation. What do we need to do first? Usually you want to retrieve the stack at the beginning of the function and then use in the body. We need to allocate a VK application info, but in order to do this, we need the first to, for our application engine name, allocate some native space, and then allocate this string on the native memory via stack UTF-8. Then we call VK application info. We set this type, all the string, API version 1. We go next. We retrieve the required extension. It's a pointer buffer. If it's null, then we get we know we are in an error state. Then we create a VK Instance create info also will require an instance type, and then we pass our application info we just created. Then if this required instance extension is not empty, and the user want to have validation, then we need to allocate, we need to take the pointer buffer and then make space for another slot, and then copy back all the stuff, and finally allocate the new extension, like we are doing here. So we copy all the extension from the required extension to the instance extension variable. We allocate the VK debug utils, then we actually put it, and then we set the variable. Otherwise, we set immediately the variable of before, because we didn't have to add a new extension. Then again, if we need validation, then we need the VK layer kernels validation, which has all the current validation functionality. We want to check if this is available. So basically, we retrieve all the instance layer properties in this way. You create pointer to nanita to retrieve all the layer properties count, and then with this you can actually allocate all the buffer for the layer properties, and then retrieve finally all the layer properties. Then we check if this layer is present. If this is present, then we simply allocate a pointer buffer. We give this validation layer name in this pointer buffer, and then we assign to the corresponding variable. If not, we fire an error. At the end, we create a pointer buffer where will be saved the instance pointer. So we call vcreate instance, and we pass at the end our pointer buffer. We will get an int at the end. Then we will create our VK instance. We pop the stack, and we return the result. Create instance. So with VK2, we can just do this. Create instance. We return directly an inline classes. It's everything on Java. We don't want to deal, we already take the hit of the performance since we are in JVM. I don't want also to take the hit about writing, let's say, I will not say hardly, but bear with me on this. So I don't want to write all the boilerplate code. So application info, hello triangle, my engine once. No need to deal with pre-string and so on. I don't have to type also I don't have to specify the type. So then I get the required instance extension. It's one unique array list of string. I want to avoid the nullability. So just if it's empty, I'm in the failure state. Then I create the instance create info. If it's not empty, if I want validation, I just add the string into the array list, and then I simply pass the array list to the corresponding variable. If it's validation, VK layer kernel validation, with just one line, we retrieve all our layer properties. All the boilerplate code is again hidden by the library. We check if it's present the layer. If it's present, we simply add them. Otherwise, we fire the error. And then we create the instance. Again, no pointers, so we don't have to create a pointer buffer and then retrieve from the pointer buffer after calling the function. It's a direct instantiation, and there is no allocation function, because I never saw anything about passing something for the allocation, so this is always null. What is the expecting VK result? Well, since everything is in line, we can just call the function that it's a dummy constructor, and then also accept a lambda at the end. It's in line, so we can write return, and in the lambda we'll be given the result. At the first one, we return the instance. What happened to the stack? Well, you remember we had to create the stack once and then use inside the code. Here, what we do, basically, we use the stack just in two places, where we retrieve the layer properties and when we get the instance. This will be all automatically done. I mean, if you don't pass in this way, the stack will be retrieved. You will get the hit of the stack get twice. If you don't want to get this hit, then what you do, you basically call create instance using the memory stack as a receiver. So everything nice, very few modification, and it's really efficient because in the hot loop you don't want to pay an additional hit, so you should pass the stack that you get all through down the stack function where it's needed. All the libraries are available at github.com under Kotlin graphics organization. Sorry, I don't have time for a question and answer, and I hope you will find some interesting stuff over there.
Yeah.